So this is lecture number 6, Introduction to Robotics Engineering 4161, or ECGR 4161, you know what it is. All right, so the discussion was batteries and battery technology. Just for grids, let's look at a battery subsystem. Assuming that this is your bag of goo associated with a with your battery. So you electrical and computer engineers, what else do you need on this?
An electrolyte.
It's in the bag of goo.
Oh, voltage regulator.
This will be a block diagram model.
Need a voltage regulator.
Voltage regulator? Okay. Let's assume that this is a regulator subcircuit. What else do you need?
Wire harness. Temperature sensor.
All right.
So the current sensor.
We'll call this a bag of goo. I think that is an official term. All right. And this is going to be a safety circuit. The safety circuit has already been identified. One thing is a temp sensor. Why do you need that?
Doesn't blow up.
So it doesn't blow up, explode, overheat, expand beyond what it should be. What else do you think is going to be on there?
Current, overcurrent protection.
All right, a current protection circuit. Why is that?
Short circuit from both up.
All right, short circuit. But what else?
Overcharge.
So you prevent overcharge. I should probably be writing this on paper. And over discharge. Anybody know what a measure of charge and discharge is for a battery?
Hours.
That is the standard identification of a capacity of a battery, right?
Watt.
C.
C, right? Like AC batteries.
So C is a capability of its storage capacity and its ability to be charged and discharged. If you exceed C, it overheats and is not good for the battery chemistry inside. All right? Why is that important for us in robotics?
To protect the battery, make it last long.
All right? Battery so it lasts long. You were saying something, Susie?
So we don't melt it?
So you don't melt it? So imagine this. Remember I talked about that underwater torpedo-like thing? I don't think it looked like a Concorde, but... All right? If that's underwater, are you tethering it with a wire? No, right? So it's got to have a battery inside. By the way, do you want salt water to wash over your battery and cool it?
No.
Usually not. So what do you think you're stuck with in there? A small enclosed container that if you want to cool the battery, how do you think you would cool the battery, mechanical engineers? Say that louder.
Circulate air around it.
All right, do you think you have a lot of air inside?
No.
Air is volume, volume is wasted if it's in there, right? Plus it's also adds buoyancy, which you may or may not want. So mechanical engineers have had thermal, come on.
Build a heat exchanger.
All right, a heat exchanger, what's one of the easiest ones?
Heat sink.
Heat sink. Because what is the likely temperature of the outside of this casing?
Cooler.
Colder.
A lot colder than the inside for sure, right? So any way you can grab heat off of this battery and get it contacting the metal of the outside, you're in good shape. All right, so getting back onto this. Safety circuit, temp sensor, circuit protection. So, by the way, is it efficient to use a regulator?
No, it adds an efficiency.
All right. So, for those of you computer engineers and electrical or mechanical engineers who may not have had a lot of, is this in 3132 or is this in some other course? It's not in that? All right, so a voltage regulator works by what? Taking a higher voltage and stepping it down. You could also have a, was it a buck converter to boost it up?
Increase.
All right. So is a voltage regulator helpful? Because what is a voltage regulator? It's a transistor, right? That bleeds off or drains or lowers the voltage. So what would be more efficient or effective?
The right battery.
Instead of just a regulator, there are specific devices called DC to DC converter. These are much more efficient than just a regular voltage regulator, which will take 9 volts down to 5 volts or something like that, because it has built-in electronics to lower the voltage without sacrificing current supply and without sacrificing or without generating much heat. And DC to DC converters are actually rated as to their efficiency. The more you pay, the more efficient it will be. All right? So, do you think we can hook this up to a DC to DC converter directly? Okay, we'll say yes. So, what else do we have to have in our energy system here to make it complete and smart? Hint, smart.
Some sort of metering.
I heard metering, I heard switching, which means what?
Diode in, diode out.
All right, we need to have, in here, I'm going to do this over here. This will be a microcontroller. So you're going to have charging control. And so you're going to need some sort of technology that will be able to, oh, by the way, DC to DC converter. So if you charge these batteries over here, what else are you going to need? Well, you're going to need an AC to DC converter, or you may have your wall board outside, right? So, charging control, and so you're going to have a safety circuit interface, because if you have the safety circuit here, and this will be VCC, or this will be V as well as ground, right? So here you're going to have some sort of control, and your microcontroller will monitor how you're charging, which means you're also going to have to take a look at any of the current coming in through here. You're going to have to be looking at temperature, and most likely the safety circuit will also identify anything associated with, as I said, temp and charging. And when to stop it. And typically, it also identifies remaining life. When I mean life, I mean capacity. So think about your cell phone, right? Or your mobile phone. How does it know that you're getting towards the end? So what do you think it's measuring?
How much power, or how much energy has been drawn from
All right, how much energy? How do you determine how much energy you've taken out?
a meter over time.
What is that called? Typically, you have something called a Coulomb counter, another type of device or circuit that will help you identify what you've drawn. You could also, based on a measurement of voltage, you can identify what the voltage is, and at a certain voltage, most electronics don't like to work, right? Depending on what you're creating. So, here's a nice big conversation of one of the technologies of robotics that I didn't think I would be covering, but oh well, no, I did. And this is associated with the robotics that you're going to be doing in the real world. MEs, you probably have to know something about this. Compies, you got to know something about this because you got to program it, right? Double E's because you have to create the circuits. What the heck, MEs are going to create the circuits. They're good at that, right? All right, that was a long answer to a question, wasn't it? That'll teach you to ask questions, won't you? All right, any other questions? Oh, you really aren't going to ask them, right? All right, today we're going to talk a little bit about Lab 2 and then look at locomotion. I can guarantee you that there will be a pop quiz. On Wednesday. What do you think it's going to be on?
Locomotion.
Lab 2.
Flavor of donuts delivered.
How about this? There will be a double reward. If you get a 8 or higher on your quiz, you can have donuts that I bring. But if you don't get an 8 or higher, then you don't get the donuts.
Is that a scratching?
Is that what?
Scratching, please.
I can't hear you.
Scratching, please.
Oh, yeah, that would be the scratching quiz. This is like double jeopardy. Not only do you get a bad score, but you don't get a donut, right? So, I would recommend at the very least you finish the Sakura stuff. So, without further ado, let's take a look at some of the Sakura stuff. How many of you have actually touched the Sakura board? Or at least you've started. Okay, let me rephrase this again. How many of you have actually taken the Sakura board out of the box, hooked it up via a USB cable, and actually run the online tutorial? Yeah, okay, that goes a little bit further than just touching it. Okay, yeah, I can figure this all out. In case you have a desire to look at some of the old recorded lectures, here they are. These are not widely available. These are private, so unless you have this link, you can't do it. I will post these notes up on the web later today. And so if you want to go look at some of the old lectures, you can look at that. And as I mentioned before, lecture 3 disappeared. And I'll blame Ben.
What are you trying to hide?
Actually, I think Ben did most of it. That's what I was trying to hide, right? Actually, that would have been a good one because that would have been the demo. But you guys already know what's going on with that. So, Sakura Cherry Blossom is a Arduino-like board which was developed in Japan. It uses the RX63N microcontroller. This microcontroller is heads and tails way beyond an Arduino Atmel processor. The processor itself has, I think I mentioned this before, 512K of memory and of flash and 128K of RAM. But more importantly, it runs at 100 megahertz, and an Atmel runs at 8, maybe 16. Wow. But this is a 32-bit processor, and an Atmel is 8-bit, which means it's going to take a long time to do anything, as long as what you're trying to do is computationally intensive. Now, of course, if you're running a robot and just doing simple wiggling of lines, nothing's going to happen, right? Or let me rephrase this again. it's not going to take that much processing time to do that. So Sakura would be still overkill, but you know what? Hey, it's free, so we use it. How many of you have done Arduino code before? All right, a couple of you. So if you were to look at this, would this make sense? So for the rest of you, oh good, we'll let, okay Tyler, explain what each one of those subroutines does.
You're setting the LEDs as output, initializing the push button as an input. Then you're reading the state of the push button and checking to see if it's actually pushing.
Now the assumption is that all of you have done a C-like language before. For double E's, that is definitely true. For compies, you've had C++, it should be the same thing. For MEs, you've already done Arduino, so you know what the Arduino language looks like, right?
Some of us.
Some of us? Okay. Do I need to go over basic concepts of programming associated with functions and inputs and outputs and stuff like that? Everybody knows that? If you have a question, you better raise your hand now or I'm going on.
I would appreciate it. Yeah.
Okay. The general concept in computing, as always, is if we are identifying functionality in a program, typically you have what's called a function. You start a function by first identifying what its return value is going to be. You know, this would probably be a lot better if I had a pen. And there's a pen here, but it doesn't, I don't like the way it works. Let's see if I get lucky. And it flashes when I press it, but I don't think it's working. All right, so the return value. Void means you're not returning anything. If you put int there, that means you're going to return an integer value. An int, for our processing purposes, is a 16-bit number or a 16-bit value. In this case, since we don't identify it as, is it a positive only number or is it a positive or negative? That means its range is going to be anywhere between, see how well you know this?
Negative 2 to the 16 and 2 to the 16.
It'll be negative 2 to the 15th
That's what I meant.
to positive 2 to the 15th minus 1. So what is 2 to the 15th? That's like 32K, right? And this is positive 32K. So in this case, we have a name of our function. Initialize LEDs is the name of the function. You are passing into it nothing. Passing means you give it a value, integer, or float, or character, or whatever. It just so happens that this is the name of another function. In particular, this function, pin mode, means that when we have our Arduino, there will be a numbered pin out here, and the pin will be 0, 1, 2, and it just so happens that down here there are a couple of LEDs, and the name of those will be pin LED 0, pin LED 1, pin LED 2, etc. And all we're doing is we're setting our LEDs over here, which are already manufactured on the board, we're setting them as to be outputs. And there's another pin over here called switch, and on the board there is a switch fact, here, I think it's on the picture. There are two switches here, and it's just setting up that picture, or I'm sorry, it's setting up the one of the pins to be an input. And so this function starts with the curly brace, ends with the curly brace. Here does simply what it says, initialize the LEDs. And by the way, it also initializes the push button switch. The next one is a function called button press. No input. And it's going to wait for this pin right here. Or I should say, it will check this pin for the switch. So it'll check the switch, and if the switch is equal to high, it returns 1, otherwise it returns 0. Now, this is where I yell at the software engineers who wrote this in the first place. What does high mean? What does 0 mean? And what does 1 mean? So in this case, if you're going to write code, it would be really helpful, just like you said, output right here. Wouldn't it be nice if this were like something called pressed? Then you return pressed. Because in the end, somewhere, there would be a definition of the word pressed, which means 0 or 1. And then 0 could be not pressed. Let's go to the next picture. Does that answer your question? Or did I make you more confused?
Yes.
Okay. Here's another thing too, is since we are using the board here, which is the RX, and it looks like an Arduino, there is an include file called RxDuino, which is available when you go to our compiler. Our compiler actually sits out there in the web space, and you get to it using the oh, they don't have it here. It's in the tutorial. It says the specific name. Do you remember what it is off the top of your head?
No.
So in the tutorial that's posted on our Moodle site, just go there and take a look at it. All right? So what I'm going to do is we're going to take a quick break right now. And I want you, between you and a lab partner, I want you to look at this and tell me what this code does. All right? So let's pause the tape and spend the next 5 minutes. All right, we're back. So, my fair friends. So, do we pass anything into it?
Yes.
An integer called count. All right? And this is not like Sesame Street count. 1. That's pretty good. So what does that percent sign do?
Modular.
All right, modulo, which means it's going to find a remainder, correct? So it's apparent that this is going to take a count and do what with it? Turn it into a binary digit. So the assumption is it's going to look at the last 4 digits of a binary number, right? So obviously, if you have something greater than what?
15.
15, then it will be the same thing if it was from 0 to 15, right? So it just ignores everything above 15. I just heard somebody's phone buzz.
I'm trying to email this picture to them.
Oh, okay. To me.
Oh, okay. Well, you are on my reply list.
Oh, okay. So the calculation up there will identify which LEDs, and oh, by the way, which one is the 1's digit, the 2's, the 4's, and the 8's?
B1's the
B1's the what?
the 8.
Are you sure?
The one.
B1's
B1's the,
It is.
B1 is
Right.
off to the right. Yeah. 4321.
So which one is it?
Top.
Depends on whether you're going left or right on the display.
All right, assuming that 0 starts on your right-hand side.
To top.
Well, then they'll have to leave.
All right. Which, when I look at this, why in the heck would they call it B1, B2, B3, and B4 when it's LED 0, 1, 2, and 3? All right. This is another example. By the way, this is a tutorial that somebody else wrote. Actually, I think
Ben or
Anthony wrote it, didn't he?
Anthony did, yeah.
Yeah. So we'll beat up Anthony when we'll say stuff. And this is exactly the reason why you need to make sure.
Consistent.
What does B mean? What is, B1? Why aren't you using real words? So when you program, use real words. All right, obviously, or maybe not obviously, digital write is what? A function which, if it's named correctly, will write a bit out to a port. And when we're talking about a port, we're looking at a specific pin. So in the world of microcontrollers, it just so happens that they have 4 pins that are tied to an LED and most likely tied to a resistor and ground, because remember, you have to have a resistor with an LED or with a diode or with an LED, because otherwise you'll have infinite current and you'll burn it out, theoretically, and in practice almost all the time. And of course, we started and ended our function. It returns nothing, but doesn't have an output. Yeah, obviously, these will output something to hardware. So now that you have that general concept of outputs and inputs, you can look at something like this. So if you have, in the world of Arduino, if you say void loop, this will be which was, or this would be which in the C world or C++ would be what function?
Main.
Main. So this is repeatedly executed forever. You will never leave this in your Arduino world. So obviously this says, while the digital read of the switch is high, then light the LEDs this way, otherwise light the LEDs this way. And actually, if you think about it, this is a while loop, which means that if this is high, will it ever go to this next part of the next part of the code? If you're still holding the button down, for example, if you press the button, assume that it's going to be high. So if you're holding the button down, will this code right here ever execute?
No.
No, because you have this while loop that while the switch is high, in other words, you're still pressing it, it will always execute this code right here and then loop back up to the while loop.
It's also a single equal sign.
Oh, look at that! I remember what I did with this.
Remember, C.
This is, I showed in my class
What not to do.
that this is the most common error. It should be equal, equal, which is look for equivalence, as opposed to a single equal sign, which is a sign. And then I tell my class that this bug right here is a bug that brought down the entire AT&T telephone network on the East Coast in, I think, 1987 or something like that. because there was a programming bug that only found itself in a situation where one switch failed, and so another switch had to take care of its traffic, and it caused a cascade of all the switches, telecommunication switches, that had been given an upload of code, and unfortunately that was the entire East Coast. It brought air traffic control to a standstill. In other words, they had no data on where planes were. So you can imagine if the internet ever went down, this country would just crash. So the answer, but don't do that. All right, so another comment on the motor driver, and then we're going to look at some code associated with this as well. We are using the motor driver H-bridge PMOD HB5. It looks like this, and as I discussed before, this is where you put in your motor power. So you're going to have one battery supply. Usually I recommend you make this one the 6-volt one. You can run the board, the Sakura board, at 3 volts. So if you look at this is where you plug the connector into the motor. And even though, yeah, I showed you this earlier, that these are driver lines that go to the motor. So if you provide current in one direction, it rotates in one direction. Provide current in the other direction, and it will rotate in the other direction. There are also some sensor wires that go to this as well. Because you have a total of how many wires here? I think it's 1, 2, 3, 4, 5, 6. Oh, excuse me. Oh man, I'm boring myself. I better pick it up. All right. So on this side, it goes to the computer control as well as computer power. So these two power pins, you will need to connect to 3 volts, and you can get that off of the board, off of the Sakura board, or you can tie it directly to your batteries. However, there are 2 other wires, the direction and enable. And so this is where I want to look at a little bit of technology right now. Oh, by the way, if you notice here, here's the 6 pins going to the motor. Here's the 6 pins going to the computer, and these are the pins associated with the encoder over here that are detecting if it passes, if the motor is rotating, and it will send the pulse. So, what's all the combinations of motion that you could have associated with those 2 direction and enable lines, right? How many motors do you have? 2. All right. So would it be fair to say that you're going to have a direction A and an enable A, and a direction B and an enable B? Would you tend to agree with that? All right. This is where I gotta ask if the mechanical engineers have had any sort of digital logic. It depends on how long ago you took 2161. All right. So this will be a little bit of digital logic. We'll see how well everybody else does. How many different combinations of that are there? There are 4 inputs, total combinations. All right, 16. How do I know there's 16? To the 4th. There's 4 different lines that you can program. Now again, these are lines, as you see from this, that are going from the computer that will drive the motors. And we know this for sure. If direction is 0, and enable A is 0, and direction is 0, and enable B is 0, what will our motors do? Nothing. There's no motion. Because, remember as I mentioned last class, enable needs to be 1 on for the motor to run. Yes, sir?
Won't you still get feedback if you're coasting from the Hall effect or whatever the attack is?
Well, you may get, if you're coasting, you'll get a signal back, but we're talking about control. We're only talking about controlling the motor. All right? So if you work in the digital world, you can look at all the combinations of the 0001, 0010, 0011, 0100, 0101. As you can imagine, this is going to get really, really tedious if I were to do everything. But that's, the point is that I'm going to make you do something. And that's going to be the next time I turn off the camera and let you all determine what the remainder of this table is going to be. Enable B is on. By the way, our definition, and I can't remember what it is. Do you remember for direction, which is counterclockwise or clockwise?
No.
You know, I forgot. So let's assume that if the direction is equal to 0, the direction of the motor, if you're looking at the spindle, is going to be counterclockwise, all right? And if your direction is equal to 1, then your rotation around the spindle is clockwise, all right? Oops. Clockwise. So, what's going to happen right here? Oh, and if we're looking at the robots, and that's the center pivot thing, this is going to be motor A, and this is going to be motor B. And that's looking down from the top. So let's see. If we're looking into it, that means there, right? Is that from physics? You know, the magnetic field and crap like that? Oh man, how quickly you forget physics. That was in my Halliday and Resnick book. That's all, you know, that's all I have to say. All right, so enable B. It's on. So motor B over there is going to turn. All right? What is the robot motion going to be when B is enabled but it's in direction B?
Circling around wheel A.
All right? It's going to circle. Which way is the entire robot going to go?
Clockwise. Clockwise circle.
All right? So do you agree that in that first situation, the whole robot is going to pivot clockwise on the A wheel?
As long as the spindles are facing out.
And that's a good assumption. Pivot, the spindles are pointing out. Clockwise on A wheel. All right? We'll do another one just for grabs. Hey, what happens in this case?
No.
Nothing. That was kind of cheating, wasn't it? All right, so what about this one right here?
Counterclockwise.
All right, it will pivot counterclockwise on the A wheel. You know what, I'm going to make this a quiz. Did you say? So the quiz is, finish this table for all 16 inputs. So that means take out a piece of paper, draw me all, and this is with your lab partner. So that makes it easier, right? Do you want me to do one more?
No.
Yeah.
Yeah, that's not enough, but.
Somewhere down here,
There you go.
1111.
Is that if the,
Are both motors going to move?
Yes.
Yes.
Are both motors going to be running in the same direction?
No.
They will both be going clockwise.
That's
But when the two motors, which have spindles facing outwards, both go in the same clockwise or counterclockwise direction, what does that mean? It spins in place, correct? Which way will it spin in place? So this one is spinning clockwise, so that means this side is moving forward, right? This is clockwise, that means that side's going back. So the whole robot is spinning counterclockwise, correct? So this would be whole robot. Spins in place. Counterclockwise. Why am I having you do this? Why am I having you do this?
Because we're gonna have to figure it out.
Because you're going to have to figure it out when you program. So, no better time than to have you do this. If you can pause the tape.
Why? There we go.
So we have an answer from somebody and a very nice setup of the problem.
Video's still off.
Pardon me?
Video's still off.
Oh, sorry. Why does this look so dark? Oh, I know why. Somebody has messed with the brightness. Oh my gosh.
Is it there now?
No, you gotta hit this. All right, here we go. Oh, you did the opposite direction of A and B. Why?
Forward, because that's how the robot's set up.
Oh,
That's how the robot's supposed to be set up. Plus, I wrote it in pen before you changed it.
all right. So everything's gonna be backwards on this,
No,
right?
just the forward and reverse it back.
All right, just forward and reverse. Well, the main one is, okay, when you have the direction opposite and both of the enables, then it will move. So in this case, B over here is going to be spinning clockwise or counterclockwise? Clockwise, right? So the wheel will be going forward, so the whole vehicle will go forward. In this case, counterclockwise, the wheel will be going towards the front. So yes, that is forward. Contrast that with when you have the both enables bits set and the opposite of the direction for A and B, and then it will go full reverse. All right?
So is there a way you control the, how fast it rotates, other than pulse modulation?
Is there a way to control how fast it goes other than pulse width modulation? And the answer to that is no, you use pulse width modulation. What a wonderful segue into my next part of the talk. I'd say I couldn't have paid you more with donuts. So let's take a look at a sample piece of code. And this is going to be, for those of you who were in programming classes, I am going to strongly urge that you remember to do things like pound defines. Now, for those of you who had programming classes about 7 or 8 years ago, or that actually took the class and couldn't remember a darn thing from it, I would like to encourage you to use words wherever possible. So, for example, pin SW, pin switch input is an example. Or for this matter, here I've even named direction A, enable A, direction B, enable B, so that when I use it later, that variable name will be easy to understand. Now, here is the trick with respect to our microcontroller. It so happens to turn out that in my Arduino board, you have some pins. And in this pin, I can't believe this thing is stuck shut, and I had it open seconds ago. May have to ask somebody, come on. I'm gonna tear the box apart. If you were to look at your device very closely, you will see pin numbers. There you go, right at the top. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Conveniently, those are going to be identified as port 0, 1, 2, 3. So, if you were to say, I want to output a 1, a digital bit 1 to port number 0, what function would you use and how would you define it? Well, that's where we went back to this, where we said pound defined. Whenever you see the word direction A, change it to 0. That means we're making port 0 the motor A direction pin. There you go, direction A. So that means that somewhere in your design, you are going to take your Sakura board, and here's going to be pin number 0. And you will route that to your